Hello, my name is Stockton Rock. I'll be presenting this video for Dr. Delacorte's Physics 106 class at BYU, and I will be talking about the applications of photon momentum. So just a brief overview of what the video will contain. We'll talk about what a photon is, what momentum is, and then we're going to talk about how it is applicable to us today, the fact that photons actually have momentum. And the two things that I'll talk about are solar sails and cancer treatment. So there's other videos that you can watch if you want to learn more in depth about what a photon is. I'll just be going very basic so that you can have an understanding of applications of photon momentum. So photons are massless packages of energy, and they act as both a particle and a wave, which is called the particle-wave duality. And we all have seen this before. This is the electromagnetic spectrum. And all of this electromagnetic spectrum is composed of photons that have different wavelengths and different frequencies. We've learned before that radio waves have a very long wavelength and they have a low frequency and a low energy. And then we've learned that gamma rays have a very short wavelength and a high frequency, and they have a lot more energy. And the visible light spectrum is just a small part of this electromagnetic spectrum. So, what is momentum? For lack of a better term, it is basically the oomph behind moving objects. If you were to throw an eraser at me, it would have less momentum behind it than if you were to throw a bowling ball at me. And it's actually really simple the way we calculate the momentum of an object. It's just given by the equation P equals mv, where m is the mass of an object in kilograms and v is the velocity of that object in meters per second. So if we multiply those two variables together, you can actually calculate the momentum that objects have. Now the problem with this equation is that photons don't have any mass, and so they don't work in that equation. And I'm not going to go into how scientists discovered ways to calculate the momentum of a photon, but the equation is given by P equals h over lambda, where h is Planck's constant, 6.626 times 10 to the negative 34, and lambda is just wavelength. And so we can actually calculate the momentum of individual photons as well as groups of photons given this equation. And it's useful to us today for several reasons. The first one I want to talk about is a solar sail. So if you look in this picture, you can see a small payload here. It looks like a satellite of some sort. And then attached to it is a very large, very lightweight sail. And so the sun is back here, and the light from the sun can actually hit this sail, reflect off of it, and the momentum behind that light can actually move this satellite. And so it's a pretty cool way that we're using that today. Another way that we use photon momentum that's a little bit more close to home, I guess, for us, is cancer treatment. And I want to talk about specifically the practice of radiation oncology. So radiation oncologists use this machine, it's called a linear accelerator, to treat cancer. And I will talk about how they work and a little bit of the physics behind it. They're pretty impressive machines. A new linear accelerator will cost $3.5 million. And on top of that, you have to pay $750,000 to build it's really like a bunker. It's a concrete vault that you put them in, and these concrete vaults have 6 to 8 feet thick of concrete in every direction. I'll talk about why that's important here in a second. So linear accelerators, they're very complex machines, and they produce X-rays, and that's why the 6 to 8 feet thick walls are so important. It's because X-rays are getting shot out of this machine. And so kind of an overview of how it works is a radiation oncologist will see a patient, will figure out what kind of cancer it is, and depending on the cancer type and where it is, the radiation oncologist will prescribe a specific amount of radiation. And then someone else called the dosimetrist, and who has a PhD in physics, they will actually design a treatment plan that can take that amount of radiation that the radiation oncologist prescribed, and it actually designs how it's going to enter into the tumor. And so this is kind of the guts of a linear accelerator, and so we'll just talk about briefly how they work. And the main parts we're going to talk about are a magnetron, electron gun, waveguide, and a tungsten target. So we'll just kind of go through those. So the first step of a linear accelerator is the electron gun. So we're going to zoom in here on this part of the linear accelerator to what's called the tungsten filament. So this is just a coil of tungsten metal, and they run electricity through this tungsten filament, which heats it up, and that produces electrons. And the electrons are then sped down this waveguide, this long hollow tube, because of the magnetron. So this magnetron is here to produce radio waves, and it sends the radio waves down this pipe, and it comes up and it hits the electron gun, and then it shoots it down the waveguide, and it shoots these electrons down the waveguide at almost the speed of light. And while it's going through the waveguide, the electrons are concentrated to a fine point, and that also occurs up here in the head of the linear accelerator. And these electrons are sped up almost to the speed of light until they hit this small cylindrical disc, which is also tungsten. So here you can see the electrons hitting the tungsten target, and this orange cone that you see is actually X-rays, radiation. So this cone obviously is too wide. It's going to affect healthy tissue, not just the tumor. And so linear accelerators actually have these tungsten plates, and they can move freely. And so as this linear accelerator rotates around a patient who is sitting on a stationary bed, these tungsten plates actually move and absorb this part of radiation that we don't want to hit the patient, and it can create this outline of the patient's tumor. So as this moves around the patient, it can actually change shape so where it's always hitting the patient's tumor and avoiding the healthy tissue. And so because photons have momentum, they have oomph behind them, they actually do damage to cancer cells. And there's several ways in which it can cause cells to die, or cancer cells to die. So the first is apoptosis. That's just normal cell death, but that can be mediated through this radiation. Necrosis is caused by injury. So if you've got these tiny packages of energy that are ripping through this tissue, obviously it's not going to be able to survive that, and so it can die from that. Senescence is when a cell has the inability to divide. So if you're damaging the DNA enough and the different checkpoints of mitosis can't be met, and the cell can't divide, then it's just going to die. It's not going to be able to keep moving forward. And then the last way is called mitotic catastrophe, where if you're damaging the DNA enough and messing up the cell's checkpoints, it can try to divide prematurely, actually, and that will also lead it to death. So it's a pretty cool application of photon momentum, saved countless lives. So here are my references for the video, and thank you for watching.